Hey guys, today we're going over Chapter 3, Section 3, Position Time Graphs for Constant Acceleration. So we're going to sort of talk about how all the kinematics you've been learning can sort of translate into graphs, specifically position versus time graphs. So to start out, over here we have some times and some positions. So let's imagine you guys have been doing a lot of problems with drag racing. Now this is a drag racing car, all right? At 1 second, the position would be 3.7 meters. At 2 seconds, it'd be 14.8 meters. And then at 3 seconds, it'd be 33.3 meters. If we look at that graphically, you'll see that it sort of comes up and then curves. And see that it comes up and curves. So it's not linear like stuff we've looked at before with constant velocities. It's actually going to have more of a slow curve to it. Now, that's what happens when we have acceleration instead of constant velocity. For instance, if we had had constant velocity, our graph would have looked more like that. It would have just been a straight linear progression of a line. So if it's not a linear progression, it's not a straight line, like I said, that's because the velocity is not constant. Now we have acceleration. Now, that curved line is caused by something that we have seen. What actually causes that curved line is this equation right here that we've been working with. That our final position is equal to our initial position plus our velocity multiplied by our time plus 1/2 times our acceleration times squared. That t squared right there is what causes that curve in our line. And the sign of acceleration, whether it's positive or negative, is going to be based off of how the line curves if we were looking at a graph. So let's say we have a position versus time graph. And on this we have a few different lines. Let's say we have one that's that traditional linear progression that we know. One of them curves up like this and one curves down like that. This can actually tell us the sign for our acceleration, if it's a positive acceleration, if it's a negative acceleration, or if there's no acceleration. For instance, this linear progression is going to tell us that our acceleration is what? It's going to tell us that our acceleration is 0 because we have a linear progression when we have a constant velocity. Now this upward curve right here, what that's going to tell us is that our acceleration is positive. And then this downward curve lets us know that our acceleration is negative. Okay? Now, remember when we were talking about just our regular constant velocities, and on a position versus time graph, we said that the steeper the slope is, that means the larger our velocity is, right? Well, it's a similar thing with our accelerations. So we'll take this red. Now, if our acceleration looks like this, if we're going off of these red lines to find our acceleration, these are steeper, or they have a greater curve than these blue lines, all right? What that greater curve means is that it's an even more positive acceleration going this way and more negative going this way. So the more that it curves up, it's a more positive acceleration, and the more that it curves down, it's a more negative acceleration. So let's look at it in green. If I use green, and now I have an accelerate, my line's going like this, and this line is going like that, does the green line have a more positive acceleration than the blue line, or a slightly less positive acceleration than the blue line? Well, the answer would be that its acceleration is slightly less positive. Whereas here, we would say, does this have a more negative or less negative slope than the blue line? The The answer here would be that it is a less negative slope. So as we go from the right to left, we have more positive, and then over here as we go from the right to the left, it's getting more negative. All right, to try and get a little bit more of a grasp on that, let's look at this position versus time graph that has 3 different lines sketched on it, okay? We have this red line here, that's line A, the blue is B, the green is C, and this pink is D. So the first question I have is, what's our most negative to most positive in terms of x naught? Okay, so if we have a position versus time graph, how we know what x naught is that intercept, right? On our y-axis, which here would be our position axis. So our most negative x naught is going to be A here because it's all the way at the bottom. So that's going to be our most negative. Our second most negative would be D because that's coming next in the progression. So we're going to have D. After that, we have C, and then B is finally our most positive or least negative. So that's going to be the order of those for when we're trying to figure out their x naught. So for x naught, we just look at where we have those intercept points. The next thing I want to talk about is the most negative to most positive velocity. So if you remember when we were originally talking about velocity and we were discussing constant velocity, we talked about how we could get the velocity by taking the slope of a position versus time graph, all right? So what we're going to look at here is the initial velocity from the most negative to the most positive. And if we want the initial velocity, we want to look at this very initial slope right at the beginning, okay? So our most negative slope is going to be D. As you see, that one is sloping downwards, and it is sloping downwards much steeper than C is. So D is going to be our absolute most negative slope. After D, the next slope that we have in the negative direction, like I mentioned, is going to be C. So C is going to be our second most negative slope. So that takes care of both of our negative slopes. So the next most negative / most positive slope that we have is actually going to be B, because B is at 0. So now we've had negatives, like the most negative slope, the second most negative slope, now the 0 slope, which means we're going to head into positive slopes. Well, we've got one main positive slope right here, and that's going to be A. A is going to give us our most positive slope, which means that it's giving us our most positive initial velocity. Now, the final thing to talk about is the acceleration from the most negative to the most positive. So, if you remember when we were talking about those, we were saying how when it curves down, that's going to be a negative acceleration, and when it curves up, it's going to be a positive acceleration. Only one of these is curving down. The one that's curving down is this green one here, C. So that's going to be our most negative acceleration. Then the next one, well, D and A are both curving up, but what's B doing? B isn't curving at all. So that's going to be our next one. So we have our most negative, then we have our 0. After that, our next most positive or least negative is going to be D, because D doesn't curve quite as steeply as A does. You notice how A curves much more steeply than D. So D is going to be our next. And then finally, our most positive acceleration is going to be A, because A curves up, and A curves up steepest, all right? So from most negative to most positive of our position, our velocity, and our acceleration. We got all of that from this one position versus time graph. All right, let's do an example now mathematically. Catching a speeder. It says a speeder travels at 18.2 meters per second. The instant the speeder passes a parked police car, the police begin their pursuit. The speeder maintains a constant velocity, and the police car has a constant acceleration of 4.5 meters per second squared. Show that the police car catches up with the speeder after 8.09 seconds and determine the location where this occurs. The first thing we're going to want to do is draw a picture, all right? We're going to start out drawing a picture. So here we have a picture. We have our speeder going at a velocity of 18.2 meters per second with no acceleration, so that's going to be constant velocity. And then we have our cop, or our policeman, sitting there waiting for him to start passing by with an initial velocity of 0 meters per second. But the second our speeder passes by, our cop is going to start speeding up at 4.5 meters per second squared. Now, the next step after we draw a picture is that I want you guys to list down all of your knowns and what you're looking for. So let's do that next. All right, so here I have listed out the speeder's known and unknown values as well as the policeman's known and unknown values. For our speeder, we don't know our final position. We know that our initial position is 0. Our final velocity is 18.2. Our initial velocity is 18.2. We know that both of those are constant because our acceleration is 0. And we were given a time, but we want to prove that that's the true time. So I'm going to have time equals question mark there. Then for our cop, we have that his final position is unknown. His initial position is 0. We don't know his final velocity. We know that his initial velocity is 0 meters per second when he's just sitting there. And we know that he'll accelerate at 4.5 meters per second squared. Once again, we were asked to find the time. So in order to prove that the cop catches up with the speeder after 8.09 seconds, we need to write out the equation for the speeder and the equation for the cop. Now, previously we had done the equation of motion stuff. Now what we do is we write a position time equation. A position time equation is just the xf equals x naught plus v naught t plus 1/2 at squared kinematic equation that you already learned. So let's look into writing those equations for both the speeder and the cop. All right, so here we have just the basic full equation written out, but let's start with the speeder. The first thing we want to think about is what in here is equal to 0. What can we get rid of? The first thing that I notice is that x naught is equal to 0. So I'm going to get rid of it. And then I notice that my acceleration is also 0. So I can get rid of that entire term. And what I'm left over with for the speeder is that their final position is equal to their initial velocity times t. Now I want to do that for the police. So I'm going to look at his information and see what equals 0 for him. I notice that his position is going to be 0. I notice that his initial velocity is 0. So I can get rid of both of those. Now what we're left with for the cop is that x final is equal to 1/2 acceleration times squared. So we have a position time equation for the speeder, and we have a position time equation for the cop. Now, just like with our equation of motion, what we're going to want to do to find out when and where they meet is we're going to want to set these two equations equal to each other and solve for t. So when we do that, we're going to have the equation of the speeder, which is v naught t, equals the equation of the cop, which is 1/2 at squared. Just like previously, we want the t's to be together on the same side. So what we're going to do is I'm going to subtract over the cops. I'm going to have v naught t minus 1/2 AT squared is equal to 0. Now, when I have that, I can take out one of the t terms. So if I take out a t, I'm going to have t on the outside times v naught minus 1/2 AT, close parentheses, equals 0. So we're going to get 2 times. Our first time would result from dividing both sides by this entire term, and we would get that t equals 0, which is true because they're in the same place at the same time when the policeman initially passes the speeder. But we don't care about that time. We want the second time where they meet up, which means we're going to divide both sides by just this t. And if we divide both sides by t, we're going to get that v naught minus 1/2 AT is equal to 0. So what I'm going to do is I'm going to move this t back over. And I'm going to have v naught equals 1/2 AT. Then to get the t completely by itself, I'm going to multiply by the reciprocal. So I'm going to multiply by 2/1 on both sides to get that 2 v naught equals AT. And then I'm finally going to divide both sides by that A. And what that's going to have me end up with is that 2 v naught divided by A is equal to our time. Now, when we plug all of that in, we're going to get 2 times that v naught is pink, right? So times 18.2 divided by A, and that A is our blue A, so 4.5. And when we do 2 times 18.2 divided by 4.5, we end up finding out that they pass each other at 8.09 seconds. That is when the policeman is going to catch up to our speeder. All right, so that's our win. Now we're being asked to find our where, all right? So if we want to find our where, we take this 8.09 seconds and we plug it in to one of our equations. So I'm going to choose the position time equation for the speeder, and I'm going to plug it in there. So what I'm going to end up getting is that final position where they meet is equal to the speeder's initial speed of 18.2 meters per second times that time where the cop catches up of 8.09 seconds. When you type that into your calculator, you should get that they are going to be in the same place at the same time at 147.24 meters. 147.24 meters. All right, so this is very similar to that equation of motion stuff we were doing. However, this time we're using position time equations instead of equation of motion equations. Okay, the last thing I want to talk about is how graphs can show us acceleration and deceleration, okay? So remember that a constant downward curve is going to mean that we have a constant downward acceleration. Remember, because we talked about how when curves go like this versus how when they go like this, right? So if we look right here at this section, and we've talked about in the past how the slope is going to give us the velocity. Is the slope that we have here a positive slope, a negative slope, or is it a zero slope? Well, it is a positive slope. So that means our velocity is going to be positive. Our acceleration is going to be downward. So it's going to be negative. And then that means that if we have a positive velocity but a negative acceleration, that our velocity is decreasing in that moment. So we have a positive velocity, however, we're having a negative acceleration, which means that we're actually decreasing our velocity at that time. Then, if we look right here, we'll notice that our slope is straight. It's a constant slope of 0. Now, when we have this 0 slope, that means that our velocity is 0. However, it's still a downward curve, which means that that acceleration is still going to be downward or negative. And now our velocity has decreased all the way to 0. Finally, now we're going this way. So if our slope is now negative, that's going to mean that our velocity is negative, but our acceleration is also negative. So remember how we said that if our acceleration is acting in the same direction as our motion or velocity, that is going to mean that it's speeding up now, right? So that means that at this point, our velocity is actually going to be increasing. So here our velocity is positive, but our acceleration is negative, which means our velocity is decreasing. It decreases all the way to 0, then continues to decrease towards a negative velocity. But once the velocity is negative and the acceleration is negative, that means that our velocity is actually now going to be increasing. It's going to be getting more and more negative. So remember that magnitude is going to be growing. The negative is only a sign of our direction. All right, when you guys get into class tomorrow, you're going to have a little problem set. And remember to please ask questions if and when you have them. Ask questions. No new equations have been introduced, so hopefully things will go well. But whenever you have a question, feel free to ask me. That is exactly what I'm here for, and that's why we are doing the flipped classroom. All right, I hope you guys have a great rest of your day. I'll see you tomorrow.